Up until this point, we have focused our discussion of inferential statistical analysis on parametric and non-parametric tests that allow us to compare groups of variables or analyze the relationship between variables. We have discussed many different methods for determining if an effect, association, or difference between variables was likely the result of chance. We learned about statistical significance and clinical significance of the finding. In this lecture, our last lecture in this series, I'm going to propose to you a new concept. The concept that we could use what is known about the independent variable or variables to make predictions about the expected value of the dependent variable. Regression analysis will be our final topic under the heading of inferential statistical analysis. In this last lecture, we will view correlation and then proceed to learning about simple linear regression, multiple linear regression, and finally, logistic regression. Following this lecture, students should be able to compare and contrast correlation and regression, explain goodness of fit and how to interpret R-square, distinguish between when to use each of the three regression methods discussed, list the assumptions for each of the regression methods discussed, and describe what results to report for each regression method discussed. I want to begin with a review of correlation because correlation is the foundation for regression. With correlation, we are looking at if a relationship exists between variables as well as the direction of the relationship. If we are looking at exactly two variables, we refer to the relationship as bivariate, with bi meaning two. When both variables move in the same direction, the variables are said to be positively related. Conversely, when the relationship between variables moves in opposite directions, the variables are said to be negatively or inversely related. Sometimes there may be no relationship between variables. In these cases, the variables are said to have no association. If you think back to our first lecture in this series, the lecture on hypothesis testing, I introduced you to the concept of correlation when we discussed what is meant to accept or reject a null hypothesis. At that time, I reviewed the concept that correlation does not yield causation. In other words, a relationship does not mean that one variable caused the change in the other variable. This led us into an introduction to the concept of effect size as an objective measure of the strength or magnitude of a relationship or difference between variables, or the clinical significance. You were initially introduced to two measures of effect size, Pearson's R and Cohen's D. We continued to integrate correlation as a measure of effect size throughout the other lectures of this series. When we looked at parametric tests to compare groups, we applied the measure of Cohen's D. When we looked at non-parametric tests to compare groups, we discussed the standardized effect size statistic. And in our most recent lecture on non-parametric tests of association between and amongst groups, I introduced you to the measures of phi and Kramer's V. In summary, correlation analysis determines the existence and strength of the relationship between or among variables. The accuracy of regression analysis depends on the strength of the correlation. In clinical practice and nursing research, it is not enough to understand that a relationship exists between variables. We need to understand how much influence the independent variable or variables have on the dependent variable. Another way to word this is that we want to know what percentage of variability in the dependent variable is the result of or caused by one or more independent variables. Learning this information about the strength of the relationship between independent and dependent variables allows us to develop and outline initial thinking about how to regulate the phenomena of interest, as well as how to make practice changes that will improve patient outcomes. Stated another way, correlation provides us with the key foundational information that allows us to develop predictions for the values of the dependent variable based on the known value or values of the independent variable or variables. While there are multiple methods and tests of analysis that can be used to investigate the predictive value of an independent variable or multiple independent variables, regression is the most commonly used technique and the one that you will most likely see when reviewing scientific literature, and the one that you would most likely use if you were involved in conducting a research or evidence-based practice project. In this lecture, we will look at three types of regression analysis. We will begin with linear regression, which has an assumption of normal distribution. Simple linear regression allows us to develop an equation for predicting the value of the dependent variable based on the value of the independent variable. Multiple linear regression takes this concept one step further and allows us to examine the ability of two or more independent variables to predict the value of one dependent variable. Finally, we will look at logistic regression, which allows us to use either a categorical or continuous independent variable to predict a categorical binary dependent variable. Remember that binary means the dependent categorical variable is dichotomous, or has only two possible outcomes. The first type of regression we will discuss is simple linear regression, which helps us move from correlation or a relationship between variables to understanding the ability of a single independent variable to predict a single dependent variable. The key concept behind simple linear regression is that you are looking at the impact of one independent variable on one dependent variable. Let's start with an example to help us work through correlation and simple linear regression. We would expect there to be a positive correlation between years of nursing experience and nurse's salary. In other words, we would expect that as the years of nursing experience increases, the salary of the nurse would also increase. Since we are looking at if the salary depends on years of nursing experience, we would say years of nursing experience is our independent variable and salary is our dependent variable. Since we have two variables, we are looking at a bivariate relationship between the variables. We begin our analysis of correlation with a scatter plot, as shown in the yellow box. You can see from the scatter plot that there appears to be a positive correlation between years of experience, our x-axis, our independent variable, and RN salary, our y-axis, and dependent variable. This is where Pearson's R will come in. If you recall, Pearson's R is a standardized measure of the relationship between two or more variables. Plugging this data into statistical software, we find that Pearson's R is 0.89. A correlation greater than 0.8 is a very high relationship. As we would expect, there's a high relationship between years of experience and annual salary of an RN. However, we don't want to report just the correlation coefficient. When reporting a correlation coefficient, we always want to include our p-value. The good news is your statistical software will give you that output as well. For this data set, our p-value is 0.006. Thus, we can conclude there is a strong correlation between years of experience and annual salary, and we can be pretty certain with such a small p-value that this correlation is not the result of chance. Now, what if we wanted to predict the salary of an RN based on years of experience? I teach primarily in undergrad, and this is a common question I get from students. They want to know how much money they can expect to make starting out, after their first year of practice, after 5 years, and so on. There are also many instances where it would be beneficial for us as clinicians and researchers to predict the outcome of one variable based on a known independent variable. Enter the movement from correlation to regression. We're going to pause for a moment, and I want you to think back to algebra class. I will be honest, believe it or not, algebra was not my fondest memory, and maybe it's not yours either. But we're going to walk through this reflection on algebra together, and at the end, my goal is you will have a better understanding of regression analysis. At some point in the past, you probably all learned the slope-intercept equation of a line, which is the formula y equals mx plus b. In this equation, m is the slope of the line, and b is where the line intercepts the y-axis. If you recall from the previous slides, x is our independent variable, and y is our dependent variable. This equation underlies all of regression analysis. The idea is that if we can find the line of best fit through our data, we can use the slope of that line and our known independent variable to predict our dependent variable. This method of finding of the line of best fit is referred to as the method of least squares. If you look at the middle picture on this slide with the yellow circle and blue line, you will notice that the line does not actually pass through any of the individual data points. However, this line very clearly follows the pattern and direction of the data points. We call this line the regression line. If we were to zoom in on that graph, as is the picture on the far right-hand side, we would see that each data point is a different vertical distance from our regression line. We call that vertical distance the residual or the error. It is unrealistic to have a line that would hit all of our data points, but the line of regression should be close to most of our data points. The line of best fit is defined as a line that has the least amount of residual or error. In other words, the line that has the least amount of total distance between the individual data points and the regression line. Our statistical software will calculate this line of best fit for us. But how do we know how good this line is? In other words, how good is this fitted line as an estimator of the dependent variable based on the independent variable? Just because we have a line of best fit does not mean that it is a great predictor. Think about trying on pants. They may be the pair of pants that fits the best of all the pants you tried on, but they still may not look that great. If we have a few data points or our data are not strongly correlated, the line of best fit may not be a good predictor, kind of like if you're only trying on 2 or 3 pairs of pants. None of them may fit very well. You don't want to move forward with regression analysis if your predictors are not a good fit, similar to you're not going to buy a pair of pants that aren't a good fit. We evaluate the goodness of fit using R-square. For simple linear regression, the first type of regression we're going to talk about, R-square is simply the square of a correlation coefficient expressed as a percentage. Goodness of fit, then, is the ratio of the percentage of variability explained by the fitted regression line over the total variability of the data. The more variability that can be explained by the regression line and the higher this R-square statistic gets, the more accurate our model is. Let's apply this to our example from the last slide. We previously calculated R as 0.89, which was our Pearson's R. Therefore, R squared is 0.89 squared, or 0.79, which is 79%. This means that 79% of the variability in annual salary can be explained by the years of nursing experience. In general, the closer R squared is to 100%, the more accurate our model is going to be. The question now becomes, is this a good R squared? Sadly, there is no easy algorithm for interpreting R squared. The quality of R squared is generally based on the already available information on what you are investigating. In other words, what previous R squares have been performed and accepted. For some data, a 20% fit might be excellent. For other data, it could be very poor. Our next step is to examine the goodness of the predictor, or the goodness of the independent variable. Our model will contain good predictability when our independent variable is actually a useful variable for predicting the dependent variable. In other words, is years of experience actually a good predictor of RN salary? To determine this, we use a t-test. I don't want this to get confusing. The t-test for regression is not the independent sample t-test or the dependent sample t-test we discussed with parametric tests to compare means. The t-test for regression is its own t-test. The good news is that you will use your statistical software such as Microsoft Excel or IBM SPSS to run this t-test. You will begin, as with all tests of inferential statistics, with your null and alternate hypotheses. Your null hypotheses will look like b equals 0, or the independent variable is not useful for predicting. Your alternate hypothesis will look like b does not equal 0, or the independent variable is useful for prediction. These hypotheses beg the question, or should beg the question, what is b? B is the unstandardized beta. In other words, b is the slope of our regression line. This coefficient represents the actual change in the dependent variable y when the independent variable x increases by 1 unit, assuming all other independent variables are held constant. For the example we have been working with, this would tell us how much salary increases as years of experience increases by 1 year. You will also see beta, the standardized beta reported in regression analysis. This is a standardized measure that helps you to compare across studies, similar to how we discussed the standard normal distribution. This coefficient standardized beta shows how much the dependent variable changes in terms of standard deviations when the independent variable increases by 1 standard deviation. This standardization allows researchers to compare the relative importance of different independent variables in predicting the dependent variable. For this course, we will be working primarily with B, the unstandardized beta, but it is important to still understand generally what the standardized beta is. As with all other tests of inferential statistical analysis, linear regression analysis has assumptions that we must check before running the tests. We will look at the assumptions of simple linear regression. The first assumption is linearity, meaning the relationship between the dependent variable and the independent variable should be linear. You will visually check this assumption using a scatter plot. The second assumption is independence. The values of the dependent variables are assumed to be independent. In other words, the subject should be responding independently. You can check this assumption using a Durbin-Watson statistic. Your statistics software will run this statistic as part of regression analysis. What you need to know for this course is that a Durbin-Watson value around +2 indicates independence. Further discussion of this concept is beyond the scope of our course. The third assumption is the assumption of normality, which can be confirmed using one or more of the methods discussed from previous lectures. You can use a histogram, a PP plot, skewiness and kurtosis, or statistical tests such as Kolmogorov-Smirnov or Shapiro-Wilk. The fourth and final assumption is equal variance, which can be checked by having your software provide a residual plot. You are looking for homoscedasticity, or a consistent spread of the data. If you notice a different type of pattern, such as a megaphone, which is shown in the bottom of the 2 yellow pictures, you have heteroscedasticity, and the data is not consistently spread, and the assumption has been violated. We will now bring together all the information we have been discussing to explain how to conduct simple linear regression. The first step is to determine if there is a correlation between your independent and dependent variables. You check this with a scatter plot and then by computing a Pearson's R and associated p-value. If the Pearson's R demonstrates a relationship and the p-value is smaller than your alpha of significance, you move on to regression analysis. Begin by checking your assumptions for simple linear regression. If the assumptions are met, you build your null and alternate hypotheses. As with all tests of analysis, you would use software such as Microsoft Excel or IBM SPSS to compute the test statistic. Remember, this is the t-test for regression and associated p-value. This information will be presented in a table format in output from your software. If the p-value is smaller than your chosen alpha level of significance, you will reject the null hypothesis and say that the independent variable is useful for predicting the dependent variable. If the p-value is larger than alpha, we will accept the null hypothesis and say that the independent variable is not useful for predicting the dependent variable. The regression analysis table output will also provide you with values for the standardized beta, the unstandardized beta, and the standard error for the unstandardized beta, and the intercept. Remember, the unstandardized beta is the slope of the regression line. The intercept is what you might expect it to be, the y-intercept. This is also the unstandardized beta for the dependent variable. Thus, you can use these values to create a prediction line for the data. This will make more sense when we apply our example on the next slide. To report your findings from simple linear regression, you can simply provide the table output from your statistical software. Your table should include the unstandardized coefficient beta, the slope and the y-intercept, the standard error for both unstandardized coefficients, confidence intervals for the unstandardized coefficient, R-squared as an overall statistic about the fit of the model. Let's look back on our example from the beginning of this lecture and go through these steps. We already computed a Pearson's R of 0.89 and a p-value of 0.006. Since our Pearson's R demonstrated a strong relationship and our p-value is very small, smaller than the standard alpha of 0.05, we will proceed to regression analysis. We check our assumptions. For the sake of this example, we will say that the assumptions are all met, and we will run our linear regression using statistical software. Our t-test statistic is 5.48 with a p-value of 0.0006. This p-value is clearly below 0.05, so we reject the null hypothesis and say that years of experience is a useful predictor of annual salary. You can see that this table also provides us with all the needed information to report. We have our unstandardized betas for the intercept and our independent variable of experience. We have the standard error for both unstandardized betas. We have our t-statistic and p-value, our confidence intervals, and our R-squared. I do want to note that this output may look different from the picture I am showing you based on the specific statistical software you are using. We can now use our output to develop a regression equation for our example. Remember, the regression equation is of the form y equals mx plus b. Y is our dependent variable. M is our slope, which is the unstandardized beta for our independent variable, or 1,116. X is our independent variable, and B is our y-intercept, which is the unstandardized B for the intercept, or 67,352. So if we wanted to know the annual salary a nurse could expect after 2 years, we could plug in our formula. As you can see, we have annual salary equals 1,116 times years of experience plus our y-intercept of 67,352. When we plug in 2 years, we would expect the salary to be about $69,584. With simple linear regression, we were interested in the ability of a single independent variable to predict a single dependent variable. However, when working with humans, such as we do in nursing, research, and evidence-based practice, it is rare that phenomena are composed of only one independent variable affecting the dependent variable. Multiple linear regression is a technique that is helpful when we want to examine the ability of 2 or more independent variables to predict one dependent variable. The goal with multiple linear regression is to find the best linear combination of independent variables that jointly predict a dependent variable. We also want to identify the lowest number of independent variables that are truly impacting the dependent variable. Having more independent variables as predictors of the dependent variable does not necessarily mean that this is the best model for the relationship. We may have independent variables that are non-significant and do not add to the predictive strength of estimating the dependent variable. Thus, these variables will be better off left out of the model because all they are doing is adding to the complexity of the mathematical calculations without adding predictive strength. There are 3 commonly discussed model selection procedures, or ways to determine which independent variables to include in your model. The methods are the enter method, the hierarchical method, and the stepwise method. The enter method is the default method in regression analysis, and it forces all of the independent variables into the model at the same time. This is a very rough estimate of the data and will likely not be the best model because it includes all possible independent variables that may be impacting the dependent variable. The second model is the hierarchical method. This method assesses the impact of demographic variables on the dependent variable and then adds independent variables of interest to see how these will impact predictability. This model is beyond the scope of our course, so we will not discuss it further. The model that you will most likely see in practice is the stepwise method. The stepwise method allows independent variables to be added or removed from the model based on predetermined statistical criteria. Generally speaking, variables that have a p-value of less than 0.05 should be added to the model, and those with a p-value greater than 0.10 should be removed from the model. The stepwise method can be performed using forward or backward selection. With forward selection, we begin with an empty model and add independent variables based on those that are most significant, or those that have the smallest p-values, provided the p-values are less than 0.05. With backward selection, we start with all of the independent variables in the model and remove those that have the least predictive value, provided their p-values are greater than 0.10. Simply stated, in the forward method, you add all the independent variables that have a significant p-value less than 0.05, and backward, you remove all of the non-statistical variables with a p-value greater than 0.10. There is a third method called stepwise selection, which is a combination of forward and backward. In this method, the model starts empty, and you add the most strongly related independent variable, then the second most strongly related independent variable, and you see if having both variables increases or decreases your predictive value. If it increases, you keep both. If it decreases, you remove the second independent variable, and then you continually add other independent variables and reassess if the predictive value has increased or decreased until all useful values are included and all non-useful values have been omitted. Multiple linear regression has all the same assumptions as simple linear regression, plus the additional assumption of multicollinearity. Multicollinearity occurs in a regression model when two or more predictor variables, the independent variables, are highly correlated with each other, making it difficult to determine the individual effect of each predictor on the outcome variable, the dependent variable. This often occurs when two independent variables are measuring similar concepts. The question arises as if the variables are actually measuring the same thing. To test for multicollinearity, you would calculate a Pearson's R for each set of two independent variables. A Pearson's R greater than 0.85 means multicollinearity exists. To handle this, you should remove the redundant variable. There are other methods to address multicollinearity, but they are beyond the scope of this course. Computing and reporting multiple linear regression is an extension of computing and reporting simple linear regression. The first step is to determine if there is a correlation between your independent and dependent variables. You check this first with a scatter plot and then by computing a Pearson's R and associated p-value for each independent variable of interest and the dependent variable. If the Pearson's R demonstrates a relationship and the p-value is smaller than your alpha level of significance, you move on to regression analysis. Begin by checking your assumptions for multiple linear regression. These are the same as the assumptions for simple linear regression plus multicollinearity. If the assumptions are met, you build your null and alternate hypotheses, which you will note are the same as for simple linear regression because we are looking at each independent variable and analyzing each independent variable's individual predictivity. As with all tests of analysis, you will use software such as Microsoft Excel or IBM SPSS to compute the test statistic. Remember, this is the t-test for regression and the associated p-value. This information will be presented to you in a table format. If the p-value is smaller than your chosen alpha level of significance, you reject the null hypothesis and say the independent variable is useful in predicting the dependent variable. If the p-value is larger than alpha, you accept the null hypothesis and say the independent variable is not useful for predicting the dependent variable. Reporting the results of multiple linear regression is also an extension of reporting the results of simple linear regression. You should still use a table format and include the unstandardized coefficients b for each independent variable and the dependent variable and the standardized error of the unstandardized coefficients and the standardized and the confidence interval for the unstandardized coefficient and an overall statistic about the fit of the model such as R squared. The difference is that you will have a row for each independent variable. If you think back to our example, we had rows for intercept and years of nursing experience. Maybe now we want to look at other factors such as age. This would be another row. You will also report R-square and to measure the goodness of fit. R-square in multiple linear regression means the same thing as is meant in simple linear regression. The ratio of the percentage of variability explained by the fitted model line over total variability. However, R-square is computed differently in multiple linear regression than it was in simple linear regression. The algebra behind the difference in computation is beyond the scope of this course. What you need to know is that you will get the R-square for the first independent variable, and then your table will indicate how R-square changed with each additional independent variable, whether it increased or decreased, and by how much. Be sure this is included in your results table, as this will allow the reader to learn the overall predictability of the combined variables, but also the predictability of each of the individual variables. Our last topic is logistic regression. Logistic regression does not require the dependent variable to be continuous, and therefore can be used to predict group membership based on information collected from different independent variables. You often see this in healthcare as the risk of developing a certain condition, such as lung cancer, based on factors such as age, gender, race, and years of smoking history. Logistic regression is called binary logistic regression if the dependent variable is dichotomous or only has two outcomes, such as present or not present, will get cancer, will not get cancer. Logistic regression is called multinomial logistic regression if a dependent categorical variable has more than two outcomes, such as highest level of nursing education. Multinomial logistic regression is beyond the scope of this class, so we will limit our discussion to binary logistic regression. In binary logistic regression, we simplify our outcomes to numbers 0 and 1 for calculation purposes. Usually 0 represents no impact or no disease developed, and 1 represents an impact or development of some form of disease. As with all other tests of inferential statistical analysis, logistic regression analysis has assumptions that we must check before running the test. However, it is key to realize that because the dependent variable is not continuous for logistic regression, there is a different set of assumptions than those we discussed with simple linear regression and multiple linear regression. The first assumption of logistic regression is that the dependent variable must be discrete. This means the dependent variable must be measured at the nominal level so that we can predict group membership from the independent variables. The second assumption is linearity between the logit of the dependent variable and the continuous independent variable. Explaining logit would be beyond the scope of this course, but in general, a logit is the natural log of the odds that the dependent variable will occur. Thus, the linearity between the logit and the continuous independent variable means that as the independent variable increases, the logit of the dependent variable increases at a constant rate. This can be checked graphically using statistical software, and you're looking for a linear relationship similar to what you would see in a scatter plot. The third assumption is the independence of the dependent variables, or in other words, that each value is from a different person. Someone cannot both get and not get the disease. The fourth and final assumption is no multicollinearity, just as it was with multiple linear regression. You test and respond to multicollinearity in the same way as previously discussed by checking Pearson's R across the independent variables. With linear regression, we use the Pearson's R and R-squared to look at goodness of fit. However, in logistic regression, we do not have a continuous dependent variable, so we cannot use Pearson's R because, as you should recall, Pearson's R is a parametric test. There are multiple tests that can be used in logistic regression, but in general, software will print out for you the -2 log likelihood, the Cox and Snell R-square, and the Nagelkerke R-square. To interpret the -2 log likelihood, you are looking for a small value. If another model has a smaller -2 log likelihood than the model you are using, that model would be a better fit for your data. So this value allows us to compare models. The Cox-Snell R-square and the Nagle-Kirke R-square can be interpreted the same way that R-square is interpreted for linear regression, with closer to 100% showing the variance being accounted for that percentage. Let's look at an example to help us work through logistic regression. We want to find out if we can predict surgery outcomes based on gender and weight. We have a data set of 20 participants. I recognize the individual data values are very small, but this is okay because statistical software analyzes the data. Providing you with the data set is more for conceptual understanding than computation. In this model, you will note that gender is either 0 or 1. 0 is female and 1 is male. This will allow us to perform statistical analysis. Similarly, the outcomes are 0 or 1. An outcome of 0 means the individual survived surgery. An outcome of 1 means the individual died during surgery. We will begin by using statistical analysis to run our test for goodness of fit. We can't say much about the -2 log likelihood since we don't have another model to compare to. However, with both the Cox and Snell and the Nagle-Kirke, we can conclude that gender does not appear to count much for the variability of the outcome. Notice the Cox and Snell R-squared is 0.015 or 1.5%, and Nagle-Kirke is 0.02 or 2% of the variability is explained by gender. However, let's look at the goodness of fit for weight. The Cox and Snell R-square is 0.35 or 35% variability is explained by weight, and the Nagle-Kirke R-square is 0.47 or 47% of variability is explained by weight. Just like linear regression, we need to examine the goodness of the predictor or the goodness of the independent variable. In linear regression, to determine this, we used a t-test. For logistic regression, we will use the Wald test, which uses the same interpretation method as the t-test. You will use statistical software such as Microsoft Excel or IBM SPSS to run the Wald test. You will begin, as with all tests of inferential statistics, with your null and alternate hypotheses. Your null hypothesis will look like b equals 0, or the independent variable is not useful for prediction, and your alternate hypothesis will look like b does not equal 0, or the independent variable is useful for prediction. Do not be confused by b. B is not the same in logistic regression as it was in linear regression. B is the logistic regression coefficient that measures the change in the log odds of the outcome for each 1 unit increase in the independent variable. The odds ratio is the exponentiated beta, or e to the beta. In bivariate logistic regression, the odds ratio, OR, tells us the change in the odds of the dependent variable, such as getting a disease or dying from surgery, based on a 1 unit change in the independent variable, such as weight. The odds ratio tells you how much more or less likely the outcome event is for individuals with a specific predictor value compared to a reference or baseline. If the odds ratio is greater than 1, the odds of the outcome are increased for getting the outcome. For example, an odds ratio of 2.0 suggests the odds of the outcome are twice as high. An odds ratio less than 1, the odds of the outcome are decreased for the group with the predictor variable. For example, the odds ratio of 0.5 means the odds of the outcome, the odds of dying during surgery, are halved. An odds ratio equal to 1 means the predictor has no association with the odds of the outcome. We would expect this for the predictor of gender on the outcome of dying after surgery. We will now bring everything together to discuss computing and reporting logistic regression. The first step is to determine if there is a correlation between your independent and dependent variables. You check this using a -2 log likelihood, a Cox and Snell R-squared, or a Nagle-Kirke R-square. If there is a goodness of fit, you move on to your analysis of logistic regression. Begin by checking your assumptions for logistic regression. If the assumptions are met, you build your null and alternate hypotheses, which you will note are the same as for linear regression because we are looking at independent variable and analyzing each independent variable's predictivity. As with all tests of analysis, you use Microsoft Excel or IBM SPSS to compute the test statistic. Remember, this is the Wald test for regression and associated p-value. This information will again be presented in a table format. If the p-value is smaller than your chosen alpha level of significance, you will reject the null hypothesis and say the independent variable is useful for predicting the dependent variable. If the p-value is larger than alpha, you accept the null hypothesis and say the independent variable is not useful for predicting the dependent variable. Reporting the results of logistic regression is similar to linear regression. You still use a table format. You will want to include the coefficient B, the standard error of B, the odds ratio, the associated confidence intervals, and some overall statistic about the fitted model, such as the Cox and Snell R-square or the Nagelkerke R-square. Let's look back at our example for logistic regression and go through these steps. We computed a Cox and Snell R-square and Nagelkerke R-square for both gender and weight. So we already have an indication that weight is a much better predictor than gender. Note we included our R-square for weight below step 2 because we will end up getting rid of gender as a predictor. We will check our assumptions. For the sake of this example, we will say the assumptions are all met and we will run our logistic regression using statistical software. Our Wald test statistic is 1.24 with a p-value of 0.266 for gender. This p-value is clearly above the 0.05, so we accept the null hypothesis that gender does not predict surgery outcome. We then look at our Wald statistic for weight. This is 5.91 with a p-value of 0.015. This is less than 0.05, so we reject our null hypothesis and conclude weight is a good predictor of surgery outcome. You will notice a step 2 in our table. This is because we are going to rerun our logistic regression by removing gender since the p-value was so high and it is not impacting our outcome from surgery. When we do this, our p-value for weight changes slightly, but it is still less than 0.05. We can now look at our odds ratio for weight in step 2 and realize that as our weight goes up by 1 pound, our risk of death increases by a rate of 2. You can see this table provides us with all the needed information to report. We have our B's for the independent and dependent variables as well as standard errors. We have a Wald statistic and p-value. We have odds ratios. We have confidence intervals, and we have an indication of R-square to speak to the model fit. As I noted, we used R-square from step 2 for weight because gender was not a good predictor. Again, I want to note that this output may look different based on the statistical software you are using. There is one more piece of information we can look at here to help us further understand our data. On the next slide, we will discuss a classification table. While classification tables are not required to include when reporting logistic regression, they do provide us with important information on understanding the meaning of the logistic regression. A classification table tells you how accurate your classification is using the model you chose. The higher the classification percentage, the better the model. On this slide, you will find the classification table for our data set. Looking at step 1 of this data set, we are looking at data where we considered both gender and weight. This can be a bit confusing at first, so I'm going to walk you through understanding the table. We are comparing our observed survived and died to what we predicted for survived and died after surgery. So the value for the red survived row is saying that for those we predicted would survive, 11 actually survived and 1 died. Thus, our prediction of survival was 91.7% accurate. For the brown dead row, of those we predicted would die, 2 survived and 6 actually died. Thus, we were 75% accurate in predicting death. Overall, for our 20 patients, we accurately predicted the outcome 85% of the time, as shown in green. In step 2, we removed the variable of gender from the equation and looked only at weight in predicting outcomes. Notice that our values all stayed the same. This is an extreme example of the minimal impact of gender on surgery survival. But overall, this classification table provides us with a better understanding of the use of weight as a predictor of surgery outcomes. In summary, regression analysis builds on results from correlation analysis to create predictions about the variance in a dependent variable that is accounted for by the independent variable or variables. Simple linear regression is used when we need to predict a single continuous dependent variable using a single continuous independent variable. Multiple linear regression is a natural extension of simple linear regression where more than one independent variable is used to predict a continuous dependent variable. Logistic regression is essentially multiple linear regression with a discrete nominal level dependent variable. Thus, with logistic regression, we are predicting membership in a group, such as getting a disease, not the value of the dependent variable. And this wraps up our discussion of inferential statistics. I know we have covered a lot of information in these 7 lectures. What is important to take away overall is when to use each test of inferential statistics, how to analyze the results of the test. Remember, statistical software or a statistician will help you calculate the numerical values. You need to be able to understand and interpret those values either for understanding your own research results or for critically appraising the literature.